All right, so I'm going to go through a projectile motion problem in order to help you consider the starting conditions that you're given with and solve for various components that you might be asked about. In this case, we have a person who's really good at kicking things, so good that he can kick this ball at a velocity of 40 meters per second, and he does that 20 degrees above the positive x, and so it's projected to the right and up. And in this case, we're going to solve for the total range, or the x displacement, the horizontal displacement, and then we're also going to solve for what is the maximum height that this ball will reach. So looking at this, the problem that we're first faced with is the fact that the velocity we have is the overall velocity and is therefore at a diagonal. The reason why it's a problem is because we know that once this projectile becomes a projectile, once his foot has kicked it and it has this velocity, the only thing that's affecting it, because we ignore air resistance, the only thing that affects it is gravity. And gravity works vertically. Gravity does not pull things horizontally and doesn't pull things diagonally. And so when we look at this diagonal velocity, we can't apply an acceleration of negative 9.8 to it because the diagonal velocity is not going to change by 9.8, just the vertical velocity. So what we're going to do is use our SOHCAHTOA knowledge, our trigonometry, and we're going to consider the fact that, well, if I have this moving at 40 meters per second and I know that this angle is 20, I should be able to find out what is my VXO. So if my initial velocity, add a little O here, so my initial velocity is 40, then what's my VXO? What's my initial X velocity? And what's my initial VYO? And I can find both of those things using, again, SOHCAHTOA. So if I know that cosine of the angle, SOHCAHTOA, is the adjacent over the hypotenuse, and just another reminder, sine of the angle is opposite over the hypotenuse, then I can solve my VXO, which is the adjacent angle, should be my overall velocity, that's the hypotenuse, times cosine of 20, and my y should be 40 times my overall times sine of the angle. And if we do these, bust out our calculators, when we do this, we end up with a velocity of 38 meters per second in the x direction and 14 meters per second in the y direction. It's a good opportunity just to double check. The angle is less than 45, therefore we should expect most of our velocity to be in the x direction, which is what we found here, so that checks out. I've organized my different variables over here under the picture, and so I'm going to add in the ones that we just solved for, that the initial x velocity was 38 meters per second and my initial y velocity was 14 meters per second. I really recommend, at least as we start these problems, sort of laying out your different variables here. It's helpful to see what you're missing, and then you can revisit the problem and consider if there was more to the story or if there's something you should be solving for. So let's take a second and see which other ones we might be able to fill in, because a number of these we can do without any calculations at all. For instance, our initial displacements we know are 0 because it hasn't gone anywhere yet, and we're not given any weird word problem where we're like starting on the 20-yard line or anything like that. So those initial displacements are 0. Now my final x displacement's one of the things I'm solving for. That's the range. My final y displacement actually will also be 0, but the y displacement's kind of weird because maybe at the midpoint I care about what the max y displacement is. So we need to be careful about that one, but we can say that the final y displacement is going to be 0 because we know when we kick this ball it's going to come back down to the ground. So it's going to be at 0 displacement again in the y direction as well. For the x's, recall there's no air resistance and gravity doesn't pull things sideways. So we have 0 acceleration in the x direction, which means my final x velocity should actually be equal to my initial x velocity. So that's easy. And looking over at the y's, we know that gravity is negative 9.8 meters per second, so meters per second squared. So I know that the y velocity is changing by negative 9.8 meters per second every second. And if you recall from the basketball analysis we did, the initial y velocity in that previous example I did on video, the initial y velocity was equal to the final y velocity, because if we're talking about a symmetrical parabola here, where for the first half it's slowing down in the positive direction, and in the second half it's speeding up in the negative direction, if those two times are equal, then we will expect the final y velocity to be negative 14 meters per second. So we actually know a lot of these things. Don't know anything about time, we'll need that, and we don't know anything about the range yet. Okay, so time is going to be the big thing to solve for here. We know that this thing has an x velocity of 38 meters per second, but I can't find how far it's able to go until I know how many seconds it's actually in the air. And if you consider for a second a projectile, the thing that dictates how long it's going to be in the air is not so much the horizontal motion, but it's the vertical, right? Because if I take this ball and I just throw it a little bit up, it stays in the air for, just a split second. If I throw it with more force or more velocity in the vertical direction, it stays in the air longer, or even longer if I push it more. So the vertical components of this are going to dictate how long it's in the air. And that's why I'm going to look at my vertical numbers here and use that to see if I can solve for time. I know the displacements, I know the velocities, I know the acceleration. So if we turn to our kinematic equations, we should be able to find one where we can solve for time. And the easiest one in this case is going to be the Vatvo equation. So the final velocity equals acceleration times time plus the initial velocity. In this case, though, we just have to be careful because we're using the y variable, so I got to make sure I use my final y velocity is equal to the y acceleration times time plus the initial y velocity. And if we plug these in, I get negative 14 equals negative 9.8 times t plus positive 14. And therefore we can solve for time. It's going to be negative 28 divided by negative 9.8. And if we do that up, we should get that that's about 2.9 seconds. So one thing that happens, sometimes you'll get a negative time. Hopefully you recognize that that's not right. Typically it's because you dropped one of these negatives, probably the negative 9.8 or something. So just be careful of that. You can't just get rid of the negative. You should definitely go back and check your work, but that does happen sometimes. So I get negative, not negative, I get 2.9 seconds is my time. And so this ball's going to be in the air for 2.9 seconds. Now I can solve for what my horizontal displacement is. I can find my range because I know it's going 38 meters per second. So every second going 38 meters for 2.9 seconds. Just to make sure we understand sort of where that equation's coming from, we have our x monster, which was x equals 1/2 at squared plus VOT plus XO. Again, like we did for the solving for the time, we have to make sure that if I'm dealing with x's, I want to make sure I deal with my x acceleration, my x initial displacement, or initial velocity. In this case, our x acceleration is 0, so that goes away. My x displacement initially is 0, so that goes away. And now you can see why it is that the x displacement, the range, is going to be equal to our velocity in the x direction, that's 38, multiplied by our time, which we said is 2.9. So I have 38 times 2.9. And if we do this, so 38 times 2.9 gives me 110 meters. So I've now found that this ball is going to travel 110 meters. So that is a pretty strong kick that it's able to travel that far. Okay, so that's one of the goals checked off. The range is 110 meters. Now we want to consider, well, what's the maximum height going to be? And so that's what I had said before, that sometimes the y displacement can be a little bit different because maybe we don't care about the y displacement at the end, since that's obviously going to be the ground, but we want to find, well, what is the maximum height that it gets to? To help understand that, I have a different diagram here. So remember that because there's no air resistance, we have this really symmetrical parabola to the motion of this projectile. The first half it's slowing down in the vertical direction, the second half it's speeding up in the negative vertical direction, which remember is just one constant negative acceleration. So it's going to reach that top peak and stop moving up and just about to start moving down at a point where we are at half the total amount of time. So in this case, we said our total amount of time was 2.9 seconds. So if I cut that in half, because of sig figs, I'm just going to call that 1.5 seconds. rather than 1.45 seconds. So at 1.5 seconds, I want to know how high off the ground is my ball. The nice thing with the kinematic equations is it lets you solve for whatever you want whenever you want. You plug time in and it's going to give you your displacement at that time, or velocity at that time. And so if I look at the x monster but turn it into sort of the y monster, if I want to know what the y displacement is, then I do 1/2 at squared plus VOT plus the initial y velocity, and then again, remember, we're dealing with a y acceleration and a y initial velocity. And we should have all the values on the previous screen to solve for this, so I can find what the vertical displacement is at 1.5 seconds, and I'll do that by doing 1/2. Gravity is still negative 9.8. Time, now I'm going to plug in that 1.5 seconds squared, plus we had an initial y velocity of 14. So I'm going to multiply that by 1.5 seconds, and then we had no initial y displacement. And so we should be able to take our calculator and do this. We do 1/2 negative 9.8 times 1.5 squared plus 14 times 1.5, and we should get a value 9.975, or about 10 meters. And so just a quick recap of what we did here. We considered, to find the max height, we considered where will this ball be vertically, so y, at half the total amount of time, because it spends the first half going up, it spends the second half going down, so I know it's right at that midpoint that is going to reach that maximum height. When we solve for that, we get 10 meters, and so we know that our y max is 10 meters. Put boxes around our two answers, and we should be in good shape. So this is considered a full type projectile problem. It's starting from the ground. It's going through that full parabola up, over, and back down to the ground. We'll also look at cliff type projectiles, and then we'll look at some hybrid ones. In those cases, it's really just the starting conditions that change, and the assumptions that we can make about these different variables are just a little bit different. But in each circumstance, you're going to take what you know. You're going to start sort of piecing together, filling in the blanks of what you don't know until you can get to your final answer. And I'll say that in the vast majority of projectile type problems, if you're not given the time, that's usually the first thing you solve for. And once you have time, you can start piecing together, okay, how far did it go, how high off the ground, and all those sorts of things. So this was a full type projectile, and I hope that is helpful.